Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're talking about, we are finishing up our standard SC3. And you see on here, I have circled in black two things and right underneath for Unit 7. So this is Unit 7 for chemistry. And the two things that I did not teach on this standard last time was percent composition and empirical molecular formula. We're also going to have standard number 4 on this test, and I haven't stuck it up here yet because I wanted to show you this first, but it's written on your notes page. So we're going to be doing standard 4 and the finishing up standard 3. So what we're going to be doing for the rest of the year is right now I plan on giving notes every Monday, test every Friday as we finish up these little units. And you can tell it's a little unit because, for one thing, the worksheets, there were only, I think, 3 of them. The notes we're going to be able to do all in this hour. And we'll be ready for a test by Friday. So you've done the hardest thing, Unit 6, and now you're ready for the easier stuff. We're sort of going to tie everything up. So we have 6 standards. We've done 3, but it will not take us as long to do the last 3. Okay, so let's go back to our theory. How do reactions occur? What do the elements have to do for them to react? Collide, right. Collision theory. So how do reactions occur? By collision. We'll see if we can write on it today. Okay, now, so one of the things we're going to talk about are things that affect reaction rates, okay? So we already learned about in our cookie lab that cooking is a chemical reaction. Okay, so if your cooking is not cooking fast enough and you want your reaction to occur faster, what do? You're making some eggs, you're scrambling them, they're not cooking fast enough. What can you do to speed up egg scrambling time?
Add a catalyst.
You could add a catalyst, but that's not probably what you do. What do you normally do? You just turn it up, right? You add heat. So one of the things that we can do to affect a chemical reaction, these are called stressors, is we can increase the heat. So I'm going to do. Now, when you think about it with collision theory, this increases the atom's speed so they collide faster. Also, the activation energy may be supplied, and we're going to talk about what that is in a second. Okay, what about if you are you got a fire going and you want a bigger fire? What could you add to it to make a bigger fire? More stuff, right? And if it was some sort of liquid, you could have a higher concentration. You know how like you can buy the little bottle of Dawn detergent and it says concentrated, and it's supposed to be that there's less water in the bottle, there's more soap, and you pay more for that little bottle than you do for the little bottle that's not concentrated. It's got more soap particles, less water. So one of the things you can actually do to increase a reaction is increase the concentration. And we've actually done that whether you realized it or not in here. We have reacted some stuff with acid, and I controlled how the concentration of an acid is the number on the acid by the capital letter M. And so, like, there are different acids we've used, like, for example, for our last lab we did. It was vinegar and baking soda reacting, but I needed turbo vinegar. So instead of being regular vinegar that's 3%, I gave you 1 molar vinegar, which is about 17%. I increased the concentration so you got a better, quicker reaction for that lab. Okay, what's another thing you can do? Okay, so you're cooking and you want to make potatoes, and you do not want those potatoes to take an hour to bake in the oven, but you bought something new at Walmart, a new kitchen appliance that's going to speed this up to 7 minutes. What'd you buy? What is it? The Instant Pot. Anybody got the Instant Pot? They're real in style right now. You stab the potato a couple of times, you put a little water in there, and you've got that potato a whole lot faster. So one of the things we can do to increase chemical reactions is we can increase the pressure. And if you squish these particles together, you have more chance of collision. Another thing you can do is, say you've got a big piece of meat and you want it to cook quick. So instead, you cut it into little pieces. Will it cook faster? Yes, it will. The reason why is when you cut it into little pieces, what you're doing is increasing the surface area. Instead of just the outside of the steak being where it could be cooked, now you're cutting it to where all these cuts are going to expose part of what was the inside of the steak. Does that make sense to you? So it's got more area. I know it's got less area per piece, but the whole thing has more surface area. And in fact, surface area to volume ratio is always greater the smaller the piece. For example, you've got a great big Saint Bernard and a little bitty Chihuahua. You go out on a cool day, which one's going to start shivering, the Saint Bernard or the Chihuahua? The Chihuahua. The reason why is the Chihuahua's surface area to volume is so much greater. His volume is less and his surface area is greater, so he's losing more heat through his skin, and that's why he shivers. It's another thing too is corn. Do you ever worry, it's Thanksgiving, you've got a corn on the cob, you ever worry about blowing up and blowing your head off? No. But exploding corn is a huge problem. And we're not so used to this because we live in the South where we are not primarily grain farmers. And second, we have high humidity. They always say it's not the heat, it's the humidity, or it's not the heat, it's the stupidity. You ever heard that about talking about Georgia and our humidity? We have extremely high humidity because we're between the Atlantic and the Gulf. So we are just right between these huge bodies of water, and they're always supplying us with lots of humidity. Out west, it's not like that. And the farmers take the grains to the silos, and there ends up being grain dust, tiny little particles of corn or wheat, and the tiniest spark will explode them. So if you've ever lived out west and you've seen this where the farmers bring the grain to sell it, there are all these signs as you enter the place. Huge signs that say no smoking. If your car backfires, do not enter this property because any spark can blow it up. And I used to have a chemistry professor at Georgia State who was from out west, and he said he had friends die in exploding corn. Exploding grain, and that is just so foreign to us. But the reason why is because when you have smaller particles, they're more likely to react and they can explode. So I used to do an experiment. I don't know if I'll do it for y'all or not because it's a little dangerous. That you could take cornstarch or lycopodium powder and blow it to a fire and it makes a fireball. And it's very fast. It's just a flash fire. So one time I was doing that, and I had all the kids safe. I had everybody with goggles on, and it was all good. But at my old school, it was illegal to lock the door. We were not allowed to lock the door. We're here, we are supposed to have our doors locked. There it was the opposite, and we weren't allowed to lock the door. So I had it all, and I blew the fireball toward the door. At that moment, my principal walked in, and she was greeted with a fireball bigger than her. She was like, "What are you doing?" I'm like, so I was like, "I need to be able to lock this door. It's just not safe that I can't lock it during some experiments." And she's like, "You do need to." She still liked me. In fact, when I got my job here, I put her as a reference, and she tried to get me to go work for her instead, but it was too far to drive. She was like, "Please don't go work for you. Please come work for me." So even though I almost burnt her up, she was still liked me. So anyway, watch out for surface area. Okay, so the next one is surface area. Surface area, the smaller particles have greater surface area, sort of opposite of what you would think, to volume ratio and react faster, for example, exploding grain silos. And then the last one is the chemical nature. Some things are more reactive than others. Back in my stockroom, I have chemicals, and some chemicals I need to buy new ones very quickly because they don't last, like silver chloride, it loses its reactive nature because it breaks down with light. And other stuff, I have some chemicals back there that are way older than you, and they still work fine. So it just has to do with the chemical nature, how much it reacts. Okay, did everybody get that? Can I scroll? Okay. So sometimes reactions need an activation energy. Big E is energy, remember? Okay, and so this is our classic example. Here I have wood, and I have oxygen. Am I afraid that the oxygen in this air is going to start reacting with this wood and this match spontaneously combust? No worries of that at all. And so this is a diagram. This is the classic diagram that you're going to have to label on the test of a match being lit. This is the energy of the reactants, the oxygen and the match. After it reacts, the energy of the products is going to be much lower, and that makes sense. A burnt matchstick does not seem to have much energy left in it, does it? But for me to get them to react, I have to supply a little boost. So I'm going to do that with friction, causing the chemicals on the end to react. They're through reacting now, and now the reaction will keep going all by itself. Let's put this down. So now we're here. We're going down the hill. I don't have to keep striking the match. I don't have to keep adding chemicals. Now the reaction will go by itself until it's all reacted and the match burns itself out. Does the diagram make sense to you? Okay. All right, next. B. Okay, sometimes, what do we need to add? A catalyst, yes. A catalyst is something that it's not part of the reaction, but it helps the reaction along, it gets the chemicals together, and it speeds up the reaction. So it's like a matchmaker. It puts the chemicals together so they can react. An example you learned in biology was enzymes in your body. They're made of proteins. Remember that from biology? Proteins are catalysts, they're enzymes in your body, and it increases reaction rate. Okay. All right, next. This is our standard composition. Sometimes it's useful to know the composition in terms of mass or weight of the elements. For example, you've got some dirt, and you can tell this dirt has a lot of copper in it. Copper is not gold. It is not platinum. It's not the most expensive metal in the world. Do you have enough copper in this compound that it would be worth it for you to go take out a loan and open a mine and become a copper miner? Does that make sense to you? So sometimes you have to know how much of an element is in something. So is it worth it to mine it? That's our question. Is it worth it to mine it? So here's an example. Carvone causes the smell of spearmint. Spearmint oil. I like spearmint. It's one of my favorite. I like it better than wintergreen. I really like it better than peppermint. Calculate the percent composition of carvone. Okay, so what we want to know is in this chemical, what percent of it is carbon, what percent of it is hydrogen, what percent of it is oxygen. You understand the problem? Okay, this is how we do it. This is another math problem. On the test, you'll be doing this just math straight out. Okay, so you list the elements, then you write down how many you have of each one. How many carbons do we have? 10. How many hydrogens do we have?
14.
How many oxygens do we have? 1. Okay, then you find the molar mass. Where do you find the molar mass? The periodic table. What's the molar mass of carbon? Have y'all memorized it yet? It's 12. That's one of the ones you end up memorizing. What's the molar mass of hydrogen? Have you memorized that one? 1. And oxygen? 16. Okay, now you multiply them. So 10 times 12 is 120. 14 times 1 is 14. and 1 times 16 is 16. Then you add them up, 150. Okay, so this is your total mass. Okay. Now, what you do is you have to figure out the percent of each one. So how do you find percents? Just in general, in math, how do you find percent? You take what you want the percent of, divide it by the total times 100, right? That's how we did our percent last week. Okay, so for our carbon, we have 120 grams. The total is 150 times 100 is 80%. So our chemical right there is 80% carbon. For our hydrogen, it's 14 divided by 150 times 100. So it's 9.3%. And then 16 divided by 150, that's a 150, it looks like 180. 150 is 10.6%. And those are your answers. So this would be what you put a little box around. Okay, now, there's one thing you can do to kind of check it. This is not your answer, but it can check it. What should all of these add up to be? 100. So if you added them up, they should be equal to 100. Now, is 100 the answer? No, that's the check. All right, how do we feel about that? Good? Can I scroll? Nope, some people are still writing. Okay, so this just seemed a little too much with all the other stuff we learned last unit. I didn't want to add that to it. I wanted to just move this one to a different test. So this could be by itself. It's easy, but it can be confusing. For people who are struggling to figure out molar mass in the first place, this is a little bit confusing to them. Okay, can I scroll now? All right, good. We're doing great. Okay, the next one is the empirical formula. You can calculate empirical formulas from percent composition. Now, what is an empirical formula? An empirical formula is a reduced formula. For example, the formula for peroxide is H2O2. So you look at the subscripts, and if there is a number that can divide into all of them, then it can be reduced. And 2 goes into 2 and 2. So the formula for peroxide, H2O2, could be reduced to HO. Does that make sense? Now, is it the formula? No. But it's a reduced formula, and they're useful sometimes. HO is not the formula for peroxide. Peroxide is H2O2, period. Absolutely, forever and ever. Okay? But sometimes reduced formulas are useful in chemistry, and we have to know them. And they're called empirical formulas. We all cool with that? Okay. All right. So here is an example. So you have a chemical, and you know its percents, and you want to know what the formula is. So you're going to use empirical formula to go backwards from percents to the formula. And how you do that is by going through empirical formula. You okay so far? All right. So how do you do this? We have these percents, and we need to change them to grams. Okay? Now, stick with me. Think hard here. You can do it. If you had 1 gram of water, it would have the formula H2O, right? If I had 100 grams of water, it would have the formula H2O, right? And if I had the whole ocean full of water, it would have the formula H2O, right? So my amount could be anything, and my formula would be the same. Good? So to do this problem, I want my amount to be 100 grams because my percents all add up to 100, don't they? So I can take those percents and just pretend like they're grams, and then I have 100 grams of my sample, and that's convenient for me. Are we all right with this idea? Y'all look okay. All right, so we're just going to change all of our percents to grams. Why? Because we can. Okay, so first of all, we assume we have a 100-gram sample, turn them into moles. So we have grams, and now we need to change to moles. How do you change grams to moles? Where do we look for something to convert grams to moles? On the periodic table. Remember what goes with graham crackers? M&Ms. So I take my grams and I make my railroad tracks. Oh no, they didn't go away forever. They're back. What goes catty corner? What do I push down catty corner with the sound effect?
Grams.
Grams. Okay, what goes on the other side of the grams? Moles. Okay, and then this is carbon, so it's 12 grams per 1 mole. Okay, I'm going to change color so it's easier to see. So now I do the same thing with nitrogen. Nitrogen is 14 grams per 1 mole. I'm getting this off of the periodic table. Actually, I'm just getting out of my head because I've got these memorized. But if you don't have them memorized, you get them off of the periodic table. Okay, then hydrogen, we'll do it in purple. Okay, hydrogen is 1 gram for 1 mole. And then let's do green. And then oxygen, 16 grams to 1 mole. For each of them, the grams mark out, and you're left with moles. You multiply any number on top, you divide any number on bottom. We'll go red. Okay, and so we get, now this we are going to write to 3 decimal places. At this point, we don't round. Okay, so for this one, we're going to get, I guess I should do red. I should do the colors. This one is 5.302, and that's moles of carbon. Okay, now I need blue. So this one is I did more for this one, 8837. We just want lots of decimal places for this, or else you will get things wrong. So this is something we do not round too much on. So this one is 9.72 moles of hydrogen. And then we have our last one in green, our oxygen, that'll work, green, is 0.8838 mole of oxygen. Okay, any questions so far? How I got that? Okay, here's the next part. This goes back to 3rd grade. Remember greater than, less than? That's Pac-Man, greater than, less than. We look at them and we say, which of these is the least? Which number is the least? It's the nitrogen, 0.8837, right? Everybody good so far? Okay, so he's our winner. He gets a little star by him. The winner of who is less. You find the smallest, and then you divide all of your answers by that. So for carbon, it was 5.302 divided by 0.8837, and it's 6. Now, on our answers here, we're going to get whole numbers, or if it's a half, we'll do half or we'll do third. Round it to a whole, a half, or a third. Okay? Everybody got that in your head? Okay, so then the next one, we do 0.8837 divided by 0.8837. And your smallest one will always be 1, because anything divided by itself is 1. And then hydrogen is 9.72 divided by 0.8837, and that one is 11. And then our last one, oxygen, 0.8838 divided by 0.8837 is rounds off to 1. These numbers are our subscripts for our empirical formula. So the answer is C6. Usually you do H's next to C, so H11. It's just sort of a organic etiquette thing that you'll get used to. But if you put it in the wrong order, it wouldn't matter. NO. So if you write the other way, it'd be all right. But just by etiquette, usually, there's this whole thing about hydrocarbons. You are a hydrocarbon. Everything you love is a hydrocarbon. All your food, your mama, your dog, gasoline, all hydrocarbons. And so carbon and hydrogen are buddies. They go next to each other. Okay, how do we feel about that? Good. Excellent. Y'all are doing great. Okay. Those are your subscripts, and sometimes you have to multiply so there are no fractions. We'll do a worksheet to make this more clear. You already got your worksheet. Okay, and for all the worksheets I gave you, I'll put the keys on Canvas. You know you could just copy the answers down, but you won't learn. So do a problem, check your answer, do a problem, check your answers. That's how you learn math. So learn math the right way. Okay, the next idea is hydrates. Okay, some compounds have water in their crystals. For example, copper 2 sulfate has 5 water molecules in the crystal. So do y'all remember our hydrate that we dried out? We put the blue crystals in the evaporating dish and we heated them up till they turned gray, and then we added water to them and they turned blue again. Remember that, lab? That was a hydrate. You did not do a chemical reaction with that. All you did is, it's like you've got your crystal lattice, and imagine salt was a hydrate. It's not. But if it was, it would be sodium, water, chloride, water, sodium, water, chloride, water. There would just be little waters in the crystal lattice. Some crystal lattices have holes in them. You know that from when water freezes, it floats because there is air in the crystal lattice. There's air in, so it's like an aerate is what ice is. But some of them have water just embedded in their crystal. You can dry it out, and so I can buy it. When I buy these chemicals, I can buy them as a hydrate, or I can buy them anhydrous. An means not or against. So if I buy it anhydrous, I've bought it dried out. So if I'd bought that chemical we used, it would have come white gray in my bottle. Now in Georgia, with our humid air, it would quickly turn blue. But I could buy it without the water in it already. So how you can remember anhydrous, an is against, is how I remember it is anything, an and anti sort of mean the same. So like you hear Christ and Antichrist. So an is against, it's the opposite. Things that are a or against. So that's just how I remember it. Okay, so how you write it. If it is a hydrate, you write it this way. So here is our copper sulfate. And then you do a dot for times, and then it tells how many waters are in the reaction. So this copper sulfate has 5 waters bound up. For every 1 copper and 1 sulfate, it's got 5 waters bound into that chemical. Does that make sense to you? Can you imagine those little crystals? Okay. So we did that in lab and we heated it up and it turned white. Okay, now the equilibrium condition. Some reactions are reversible, and you know that because of your phones that you charge. That is a reversible reaction, like rechargeable batteries. When they stop going back and forth, this point is called equilibrium. So some of y'all have a dead phone with a dead battery. It has reached equilibrium. It is not going back and forth anymore. So that was our warm-up today. What does that symbol mean? It means it's a reversible reaction. It's something that can become equilibrium. It can reach that point. Okay? And so, chemical equilibrium is a dynamic state. Dynamic means it can change, where the concentrations of all reactants and products remain constant. Equilibrium expression is a formula, formulas are sometimes called expressions, based on concentrations in the balanced chemical equation that shows how much a reaction goes to completion. So a lot of times we want to know if a reaction can go back and forth, but then if it is under a certain condition, it will reach a point where you have a certain, in your beaker, you have some reactants and you have some products, and those concentrations remain the same. There's some reactants that are reacting and becoming products, but at the same rate, some of the products are breaking down and becoming reactants again. Can you imagine that? So how far does this reaction go toward products? Does most of it stay reactants, or does it actually become products? If a reaction goes all the way to completion, then that's one thing. But a lot of reactions don't. And a lot of times we need to know how far they will go, and there's a mathematical way to figure that out. Okay, and it is called the equilibrium expression. Now, for that, part of what you get when you do this mathematical equation is called the equilibrium constant. It will tell you how far a reaction goes. The value obtained from putting the equilibrium concentrations into the equilibrium expression from the balanced equation. And I introduced this concept to you in Unit 5. Now remember that? Well, this unit, you're going to get tested on it. Okay, so the reaction, little a big A plus little b big B, is reversible, so you have to go the other way. Whoop. Did yours go both ways on your notes already? Or you need to draw the arrow if not. Little c, little d, big D. Now, what do those mean? The little letters A, B, C, and D are the coefficients from the balanced chemical equation. The big A, B, C, and D are the chemicals in the reaction. And this will make more sense the more you do it, like always. Okay, so then this is the equilibrium constant. It's the concentration, square brackets mean concentration. The concentration of the products raised to the power of the coefficients divided by the concentration of the reactants raised to the power of their coefficients. Okay, so let's look at an example. Here we have an equation, okay, and we have nitrogen plus hydrogen yields ammonia. Now, it's a little bit more complicated than this that I'm going to teach you. Not all of the chemicals really go into the equilibrium expression, and I will explain that to you later. But for right now, we're going to learn step one before we learn the whole thing, okay? So just know I'm giving you a little disclaimer here. This is basically how you do it, but then there are going to be a few things we're not going to include in the expression. Okay, so here we have, these are our reactants and these are our products. So you start with your products and you write them in square brackets in the numerator. So I have the concentration of NH3, and then you raise it to the power of its coefficient from the balanced chemical equation. So I put a 2 right there. Then we put the reactants in the denominator. So I will put the concentration of nitrogen raised to the first power, but I don't have to write it. It's understood. Times the concentration of hydrogen raised to the third power. So in math, parentheses mean multiply. So in your calculator, you will multiply those numbers. These concentrations will be given. It'll be part of the problem. The concentration of nitrogen is this. The concentration of hydrogen is that. You have to, one skill is I want you to be able to write the expression And then the other skill is I want you to be able to substitute in to the equation and get the answer. That doesn't sound too hard, does it? Okay? All right, so this is the exceptions. The concentrations of pure solids, so like if one of our reactants was gold, just a lump of gold, you do not put it in the equilibrium expression. You also don't put pure liquids. So if there was a pure liquid in the equilibrium expression, you wouldn't put that in either. And they're not included in the equilibrium expression. This will make more sense once we do our worksheet on it. Okay, so this is our standard here that's really stressed, and it's, now I say it Le Chatelier. I know I'm saying it wrong, so just go with it. Okay, so there's this French dude, Le Chatelier. He came up with the principle, and it was that if you put a change on a system, if you put a change on a chemical reaction, that the equilibrium will shift either more products or more reactants to alleviate the stress on the system. Now that's fancy, but let me explain it to you. Say you got a cauldron, double, boil and trouble. You're a witch and you're adding stuff to your cauldron, okay? And you want more products. So what you would do is you would add more reactants, and that would push your equilibrium away from the reactants to the products. Does that make sense? And so say for your phone, you want more chemical to make more charge later, then you plug it in and it puts more electricity in it, which is a product, and it causes the equilibrium to go back to reactants, so you get more of the chemicals in your phone when you unplug it, so that it can start going back toward products again. Okay, can you kind of imagine it? So if you add more chemical, Le Chatelier, so it will tend to do the thing to alleviate the effects of the change. Let's see how I wrote it. Reduce, that's a good word. Better than alleviate. It will reduce the effects of the change. For example, if you add more chemical concentration to the products, you get more reactants in the equilibrium, and it would shift toward the reactants. That's the same thing I just said, but backwards. You can think of it like a push. It's going to push it to the other side. If gas bubbles off in the products, then there's less products. It causes a void, and nature always fills a void. Nature abhors a vacuum. And the equilibrium will shift to the products, trying to fill that void. They'll try and make more products to fill in that space. If the reaction is in a closed container, things change. You will learn more about that in AP Chemistry. Everybody come back year after next and take AP or college chemistry. Okay, so what you'll do next year is you'll take honors physics or AP physics, and then come back the year after that, and you can take AP Chem with me, and we'll learn all about the closed container and how things get more fancy. All right, how do we feel about these notes? All right, okay, you've got 30 minutes, so you can start working on your packet worksheets. While I'm here to ask questions, I'll go ahead while you're doing that, and I'll load up the keys to Canvas so that as you're working, you can check your answers. And if you get it all done, you won't have any digital day tomorrow, and you can go fishing. Okay? All right, like, share, subscribe. Science is great.